All right, welcome everyone to Physics 390 Class 30. This class is on the no-clone theorem and Schrodinger's cat. So the no-clone theorem is a result in the foundations of quantum mechanics, which says it's not possible to take an arbitrary quantum state and make a copy or copies of it. And if you were able to make copies of it, you could actually send messages faster than light and violate causality. So the no-clone theorem saves us from violations of causality. So we'll explore that. We'll also explore Schrodinger's cat, which is a famous metaphor that Schrodinger came up with to describe what's called the measurement problem, the funny situation of measurement within quantum physics and quantum mechanics. Okay, so this comes from chapters 12.4 and 12.5 of the textbook. So let's see what we got here. All right, so a full quantum state cloning machine is impossible. Okay, so here would be a cloning machine where we have a state coming in and it would be cloned and it would come out and copies of it would come out, and we could create as many copies of as we want of a given state. So what could happen if we could do that? If a device like this could clone any quantum state, we could actually get faster than light information transport. So we could send information across great distances from between the stars faster than light. So how would this work? Well, the person sending the information, who's normally called Alice, no relation to the Alice from the Honeymooners or Alice in Chains from Seattle Music or anything like that, just Alice for A. So anyway, Alice would measure the SZ state of the electron to indicate a yes. And she would measure SX of the electron to indicate a no. It doesn't matter what result she gets for SZ or SX, just which one she measures. If she measures SZ of the electron, and this is the electron coming out of a pion decay. So we have an electron coming to Alice and a positron to the receiver, whose name will be Bob. So if she measures SZ, she's trying to send the signal yes. If she measures SX, she's trying to send the signal no. So what would Bob do? Bob would take, after the Alice measures either SC or SX, Bob would take the correlated positron state. So now the two states are correlated, and he would clone it many times. So he'd make many copies of it because we have a device that could clone any quantum state. So he would clone that state many times, and then he would measure half of the clones with an SZ measurement and half of the clones with an SX measurement. And if he saw the same result for all of the SZ measurements he made, that would mean that the electron must have been measured with SZ, because it would be the electron would be in a definite state of SZ, and the positron would then have to be in the opposite but definite state of SZ. On the other hand, if SX was measured, it would be in either SX plus or SX minus, and the SZ states that Bob measures would be split, because SX plus, say, gives half SC plus and half SC minus. So then in that case, if that happened, Bob could look at the half that he measures with SX, and those should be in a definite, each in a definite state, the same state, because that would mean that Alice had measured SX of the electron, and that would put it into either SX spin up or SX spin down, which would put the positron and all of its clone states into SX spin down or spin up. So notice that it's important that Bob is able to clone the correlated positron state so he can build up statistical information from a number of clones on which state, which measurement Alice has made. If there's only one positron state, if he can't clone it, Bob can't clone it, then there's no way he can take half of the clones, because half of one is a half of a particle, which doesn't really make sense. So in any case, the result, if the cloning is possible, would reveal what Alice has measured. And if these are far enough apart, we could have a superluminal or faster than light signal sent. Okay, so so it seems like that, and that leads to problems. If we can send things faster than light, we can find a reference frame in special relativity where the receiver receives the signal before the sender sends it. So we can have things traveling backward in time, get into all kinds of causality issues. So it was proved in 1982, and I'm happy to say, I just have to say this, that one of the people who proved it, there were 3 people who were involved, but one of the people who proved it is a guy named Bill Wooters, who I actually studied with as an undergraduate. And he's a super nice guy and just such a talented physicist. But I just have to mention his name here. His name is Bill Wooters. And this is one of probably his most famous research result. Anyway, so it was proved by Bill Wooters and others, Zurich and a third individual, that such a device is impossible. That can clone any arbitrary quantum state. If so, how do we see that? If the device works for 2 states, so if it takes state psi1 and another state x, and then it turns out, so another particle, another of the same particle but in a different state, and the device turns out a copy, the original state psi1, and then a copy of psi1. So it takes psi1 and another state, which is a sort of a blank state. I mean, it's some state, but it's not, it has nothing to do with the psi1 state that's to be copied. And it turns out 2 psi1s. So if it does that for psi1, and the device also does it for psi2, and if you like, you can imagine psi1 to be spin up and psi2 to be spin down. That's a nice way to think about this. So if that's true, if it works for 2 states, then by the linearity of quantum mechanics, a device has to act through the what are called unitary operators, which evolve the wave functions in a linear fashion. So when acting on a linear superposition, psi, which would be some coefficient alpha times the first state that the device works for, plus some coefficient beta times the second state the device works for, it will actually give, if it's fed that superposition and another particle to try to copy that onto, it will actually give out alpha times psi1 plus beta times psi2. But that's not really a copy of, that's not this original state copied. That's an entirely different state. What would be a copy would be if it gave psi, which would be the state alpha psi1 plus beta psi2, and then times another alpha psi1 plus beta psi2. But that's different because when this is multiplied out, it gives 4 terms with cross terms and so forth. So anyway, because of the linearity of quantum mechanics, if it works for 2 states, it will not work for a linear superposition, a non-trivial linear superposition of those 2 states. So that constitutes the basics of the proof that such a device is impossible. Now, it is possible to build a device that can clone 2 distinct states successfully, like spin up and spin down for an electron, or the 2 different horizontal and vertical polarizations for a photon, but not more because of this problem with, or this property of linearity. This has actually led to a really interesting field, quantum cryptography, which banks, among others, and governments are now testing for unbreakable message transmission. We have codes right now based on RSA transcription, and they're based on huge prime numbers. But those prime numbers can be factored, and while those RSA codes are very secure, they're not completely secure. But these quantum protocols would be, in principle, unbreakable. So how would they work? Well, Alice would send, the sender would send a set of 4 states in some order as a key. So for her 4 states, she could choose, for, let's say we were dealing with a stream of electrons as our, what she was sent, she could choose in some order the electron to be in SC plus, SC minus, SX plus, and SX minus. So some permutation of these, if there were 10 electrons, it might be SC plus, SX plus, SC minus, SX plus, SC minus, SX minus, SX plus, SC plus, SC minus, and SX plus. So just some ordering of these states for each electron that she sends as a key. So, and then, so a code breaker named Eve, was short for eavesdropper, can't clone this key and send an identical copy on without making some mistakes. Because to do that, Eve would need to have a device which could clone 4 different states successfully. But we've seen that we can only clone 2 distinct states successfully. So as long as the code, the key is based on a set of states with more than 2, here we have 4, it's not possible for a code breaker to clone the key, keep a copy of the key, and send an identical copy on to, say, Bob, the receiver, and that Bob would get the same key that Alice sent. So there'd be some corruption because this machine or this device would not work properly on one of these, at least one of these states. And when Bob, the receiver, and sender Alice later compare their keys, they would realize that someone had tried to eavesdrop because the 2 would not match. So they could then discard that message and not act on that information. So Eve cannot eavesdrop without being detected. Okay, so pretty interesting. Okay, so a lot of this is about measurement and cloning quantum states. So talking about measurement, the measurement problem is probably the main philosophical conundrum in quantum mechanics, and it's expressed with Schrodinger's famous cat, his great metaphor for to kind of bring the measurement problem, really just put it right in our faces, and with one of our favorite domesticated pets. So what is this going on here? The measurement process seems to be distinct from the continuous evolution of the wave function according to the time-dependent Schrodinger equation. So we know that time-dependent Schrodinger equation, I'm not going to produce the equation here, but it produces a continuous evolution of the wave function, and it evolves in time. Probabilities can shift between different eigenstates as time evolves, depending on the Hamiltonian operator which causes it to evolve. Then when when a detector measures a property, the wave function which has been evolving collapses into one of the eigenstates of the property that the detector is measuring. So for example, if we have an electron going through a 2-slit experiment, and we look on the screen, the detector would be the photoplate or photosensitive screen, and all the possibilities of the wave function hitting the screen when the particle hits the screen and is observed, it hits a specific point on the screen. So it collapses into a position eigenstate on the screen. But then once that wave function collapses, then and the act of measurement has taken place, then until another measurement takes place, continuous evolution restarts from the new wave function. Okay, so it seems to be these two different processes. We have the continuous evolution of the wave function according to the time-dependent Schrodinger equation, and then this collapsing wave function, which seems to be just a separate process, and they kind of alternate back and forth when as measurements take place. But this really begs or brings up the question, just what the heck is a measurement? So, and that's where Schrodinger's cat paradox, and here's a little cartoon of a Schrodinger's cat here, half alive, this was bright part on the right, and half dead with the X in his eye, or her eye, with a nice long tail here and a drooping tail here. So in the Schrodinger's cat paradox, which you certainly may have heard of, but let's just summarize it very briefly. We have a cat in a box, and the cat will die if a radioactive atom decays. And when it decays, it actually triggers a little hammer, which releases a poison gas and kills the cat. If the radioactive atom does not decay, the poison is not released and the cat lives. So the paradox becomes that until we look, if this is a closed box, not a box we can see in like this picture, until we actually look in or probe it in some way, or listen if the cat is, meowing or not, for example, or in some way get some signal from inside the box, it seems the cat is in a superposition of alive and dead states, because the atom, we don't know if the atom has decayed or not. That's a quantum probabilistic process. And since the cat's fate is tied to the atoms, it seems as if the cat's wave function would be a superposition of alive and dead, which seems like just kind of blows your mind that, that we really think this whole cat is in this ghostly superposition of two states being alive and dead at the same time. If you're a physicist, you've heard this cat paradox many times, but it's easy to forget the first time you hear it, how strange it is and how bizarre it is, and what a great metaphor Schrodinger came up with to bring this strangeness of this measurement process to our attention. So anyway, most physicists think the cat lives or dies before the box is opened in somehow or some way. It's not clear how that happens, but they think it's just too much of a stretch to think that we have to open the box to know if the cat is alive or dead, because the cat is a big object. Maybe if it were, a tiny electron, it could stay in a superposition for a while, but cat is just too big, and it just strains credibility too much to believe that it would stay in that superposition of states. So, what constitutes a measurement, right? We say, just what is a measurement? This is supposed to illustrate some of the paradoxes that come with thinking about measurements. So various characteristics of a measurement have been proposed. Perhaps the need for a human consciousness. So when we listen and perceive the meowing of the cat, or we look in and we see the cat moving around, and that registers in our consciousness, that constitutes a measurement. Others have thought that perhaps some macroscopic classical measuring device would be enough. So perhaps we have we stick a probe inside with a camera, and that records on a film, and that would be enough to collapse the wave function of the cat into alive or dead if it's recorded on a photographic film, even if some person has not seen the film yet. That would be that camera and film would be a macroscopic classical measuring device, or perhaps just an irreversible process of some kind, some kind of something that happens that can't be reversed, which is a little bit vague in this context, but has been proposed as a necessity for a measurement. So all these have been proposed. Note that a macroscopic object like a cat or a pineapple or a baseball or whatever your favorite object is at the moment is subject to continuous interaction with just gazillions of particles from the environment, atoms and molecules banging into it all the time. And those atoms and molecules interact with it and prevent the coherence of the types of states like this linear superposition of alive and dead. So a macroscopic object can't be in a linear superposition state. That's the current thinking, is that the cat, when it's inside the box, would be in interaction with the air. Presumably there's air inside the box, so it would be interacting with all the air molecules, and those interactions would cause this linear superposition to be corrupted and destroyed, and it would force the cat to decide on its wave function or on its state, either alive or dead. And this theory is called decoherence, because coherence would mean coherent enough to be in a linear superposition. Decoherence means that we can't get linear superpositions. We get more complicated composite wave functions for the whole cat. And this theory of decoherence has been developed and well developed. There's a lot of thought that's gone into it, but it's still not fully understood. And the measurement problem itself, or the measurement process, is not fully understood. Is it something that's distinct from the evolution of the wave function, or is there some way we can, in some way we haven't thought of, unify the two so that the evolution, there's sort of one process going on which manifests as the continuous evolution usually, but when what we think of as a measurement goes on, once we understand it better, we see that that's a different aspect of some other process as yet undefined or unspecified or undeveloped theory that would unify the measurement process and the evolution. So there's still plenty of things to learn about the measurement problem. So, and it's part of what makes quantum mechanics fascinating and also frustrating at times, and difficult to understand. But I think it adds to the richness of our world, that we have this kind of essential mystery still sitting at this kind of the center of one of our main physical or our main physical theory. So anyway, just to recap briefly, what have we looked at? We've looked at the no cloning theorem, which says that it's not possible to clone an arbitrary quantum state. This protects us from having from being able to send messages faster than light and violate causality. This was proved relatively recently, about, I guess it's been almost 40 years ago now, but not in the, still about 50 years after the beginnings of quantum mechanics, or even 60 years. So it took a while to show that. That no cloning theorem and the repercussions of it, or the implications of it, are being used in quantum cryptography today. And then we looked at the measurement process and thought about what is a measurement, some properties that might be necessary for that, just exploring these ideas, because we don't have an answer to this yet. And Schrodinger's cat paradox is still with us. We don't have a full explanation that everyone agrees on. It's just agreed that it's mysterious. People have their opinions. Most physicists are fairly certain the cat lives or dies before the box is opened, but can't prove it. There's no sort of overarching theory that everyone is satisfied with. And then this theory of decoherence is very promising and is worth looking into if you have a chance. So still plenty of things to learn. Thanks for your attention, and I will see you in class.